Good evening, everyone. I'm Janani Balakamran, and on behalf of Aberdeen Maritime Branch, a joint branch of IMarEST, RENA, and ISIS, I'd like to welcome you today to the technical webinar. We have the privilege to have Mark Thomas from DNVGL this evening, giving us an insight on the wind turbine control systems for floating platforms, with focus on concepts, challenges, and potential developments. Mark is a mechanical engineer with over 20 years of experience in the design analysis of structures. For the last 6 years, he's been heavily focused on wind turbine design, analysis, and control with DNVGL. His previous experience also includes involvement with aerospace structures, composite materials, turbomachinery, vehicle crashworthiness, seismic assessment, and ship structures. So with his diverse expertise, I hope you find the presentation interesting. If there are any questions for Mark, please use the Slido system with the code #WindTurbine, and we'll try to address them at the end of the presentation in the Q&A session. So without further ado, I'd like to hand it over to Mark. Thank you.
Yes, good evening, everyone. This is Mark Thomas from DNVGL Energy. I'm principal engineer in the loads and control team, and I'm based in Bristol. And this presentation is about wind turbine control systems for floating platforms. So before we go into the main presentation, just a little bit about DNVGL, which we're at the forefront of floating wind development and have been for a number of years. So this is in terms of development of the DNVGL standards, such as ST119. We're also been involved with technical concept design support for many floating turbines, and this includes control algorithm design for those turbines. Which includes commissioning and system ID and testing. We've been doing floating wind market studies and technical due diligence for many projects. And we've done verification, which includes tank testing, support, and analysis, and independent analysis of floaters and wind farms. The final thing to mention is the software side. So within DNVGL, we develop the Blade software, and within the loads and control team, we are quite heavily integrated in that process with engineers, exchange with the digital solutions team. And the Blade software has been used for more than 20 floating wind turbine projects. In terms of software, DNVG also develops other software used for structural analysis like SESAM. Okay, so onto the agenda for the webinar. So I'm going to give an introduction to control for wind turbines, and then specifically look at the floating platform dynamics and the challenge that gives the turbine control design task. And then specifically we look at the various turbine control loops and how they're modified for a floating wind turbine. And then we'll also touch on some future developments which may happen in the floating control area. Okay, so start out with an introduction on control. So what is the wind turbine controller? So the controller is the heart of the wind turbine, basically. It makes use of the available inputs to determine the operation of the turbine and is responsible for its performance and safety. So the controller itself takes in various inputs from the turbine. So predominantly measured power and measured speed. So most of the primary control loops use the speed measurement. But these other measurements can also be used for sort of supervisory control and for defining set points for the turbine, for example. There could be some additional control loops, so which may use blade loads. So if you have individual pitch control, which is a way of alleviating loads, these would use blade load sensors or sensors at the tower top or on the rotating shaft. Another input, which is also important for floating wind turbines, is the tower acceleration signal. So we basically have a fore-aft accelerometer at the tower top, and this can be used to provide damping to the tower, or in the case of a floating platform, to the platform motion itself. So the controller takes those inputs and then works out demands for the actuators. So the main actuators used for controlling the wind turbine, the primary objective controlling the speed, are the pitch actuators, so that you can pitch the blades from fine to feather, thereby reducing the torque and thrust. And also what's known as the torque drive, which is basically a generator combined with a power converter system. So the controller can make a demand to the power converter system for the torque, so varying the resistance of the drivetrain. So this is used to help control the speed of the turbine. The primary task of controlling the speed is also affected by some disturbances. So although we're trying to maintain optimum conditions for the wind speed, there's also wind turbulence, which produces some additional dynamics on the turbine. And so the role of the controller is also to reflect those disturbances and try to maintain dynamically the speed of the turbine and alleviate the loads caused by the turbulence. There's also the flexibilities in the structure. So the flexible blades and the flexible tower and the drivetrain, these are the primary flexibilities that can be coupled with the controller and the main task of controlling the speed of the turbine. So the controller needs to be able to deal with these disturbances and manage these in the best way possible for the loads. So why is the controller important? So the role of control algorithm design has a large influence on reducing component cost and increasing the component lifetime by alleviating the loads on the structural components, but also on the actuators, and minimizing the actuator demands and travel, such as the pitch system, which can also then increase or reduce downtime with the turbine and increase reliability. So the control is a real enabler with constantly increasing rotor sizes. So when I started with DNVGL in 2007, we were looking at 1.5 megawatt turbines with a 75-meter rotor onshore, and now onshore we're looking at 150-meter rotor and 5 megawatt turbines. And in the future, well, who knows, we could be looking at 250-meter rotors and 20 megawatts. And so we can see that the very significant increase in loading, and so the role of the controller is particularly important in managing that loading. And the largest benefits with control can be obtained where the control design is integrated at an early stage in the overall design process. And this is to explore trades, say, between energy capture and loading, or between loading and actuator demands. And recently, this has been integrated with levelized cost of energy analysis to explore those trades in the most accurate way possible. So there are three main elements of the turbine controller. So we have the power production controller. So, and we'll talk a bit more about this later. So this is about regulation of the power and the speed of the turbine, and doing it in a way where we're avoiding excessive actuator demands because of the costs associated with that. We can alleviate turbine loads, some turbine load components, through managing the pitch control in particular, which has a quite large influence on the thrust related loads. And an important element of the power production control is to maximize the controller robustness against uncertainties and non-linearities. So the kind of primary design process for the controller is a linear approximation. And so in reality, the turbine can vary from that linear approximation due to those non-linearities, and also model uncertainties in the way that the model was created, and whether it the turbine in reality is different from the model. And for that reason, you need robustness so that we can be confident that the controller will remain stable in those conditions. The second aspect of the controller is supervisory control. So this typically includes logic for starting up and shutting down the controller. And this is where a lot of the extreme loads are defined by the logic in the supervisory control. In particular, the way that the alarms are set. So alarms are set for detecting faults or unsafe conditions and how those are handled, typically leading to shutdowns. And the way that the shutdown pitch rates are defined greatly influences the loads. The supervisory control can also be responsible for health monitoring and data collection. So above those two aspects of the controller, it's worth mentioning the safety system. So strictly, the safety system is not part of the control algorithm, but some aspects of the safety system are tuned to minimize the loading during the design of the controller. So generally, the safety system contains simple hardware to ensure fail-safe operation of the turbine, and it's typically activated when internal or external failure is detected, or if a dangerous event is detected, or if the wind turbine is not kept within its normal operating limits by the power production or supervisory control, then the safety system will take over and bring the turbine to a safe state. Okay, so the control design process itself, we start off with a steady state design, which is primarily around maximizing the energy capture. And this will be things like defining the power curve and defining how energy is captured in below rated wind speed conditions. And then we move on to the dynamic part of the design. So this is based around a linear model of the turbine, which may be embladed, for example. And then we use classical SISO design techniques to design the controller. And this is where we primarily look at controller performance, where we're trying to maximize the responsiveness of the controller, but also maintain robustness in case of differences between the real turbine and the model, as we've discussed. So the linear model and design is an approximation. So it's important to do full nonlinear model simulations. So this is done using bladed. And here we do load calculations where we run thousands of simulations to test the turbine in various conditions. And these design load cases, DLCs, are typically defined by the standards to test the turbine in many different situations. So then once we have a non-linear design that we're happy with and a full set of loads, we can then go on to implement the control. And the first part of this is to do factory testing. And this can test the subsystems of the controller, so the PLC and the actuators, and the various different loops can be tested real time on the bench. And then the final stage of the design process, ideally, is the commissioning. So we commission the control system on the turbine, and then do a process of system ID. So we look at the turbine data, and we run specific tests, testing subsystems like the actuators, and record data during those tests. And we can then run companion simulations using the bladed model or the model of the turbine. And we can compare the results of those companion simulations against the measurements. And the companion simulations typically would use measured wind data, and we reproduce the measured wind data in the simulation to try and get the closest possible conditions to the measurement during system ID. So this is an iterative process. So at the end of commissioning, we have an updated model of the turbine, and we can then decide whether we need to repeat any of the previous steps, if the model is sufficiently different from what we used during the previous iteration of design. Okay, so just move on to some turbine control basics. So this is an illustration of the power production strategy. So so here we're plotting a graph of rotor speed against torque of the drive, and the dotted lines represent the power available in the wind at various different wind speeds, considering the efficiency of the rotor. And so what we find is that at each wind speed, there's an optimum point, which is where you have the maximum power, which is defined by the maximum power coefficient. And associated with that is a optimum tip speed ratio. So this is means that the rotor is turning at the optimum speed for extracting energy, given the size of the rotor and the number of blades, for example. And there's an optimum CP curve for the fine pitch angle of the rotor, which is used in below rated conditions. So we basically have this steady state operating curve then for the turbine. So we have a minimum speed region, which is defined by what's required for the generator and power converter. And then we have the rated speed region here, again, defined by the generator characteristics. And in between these two constant speed regions, we have what's known as the CP tracking region, where we're following the optimum CP curve and maximizing energy capture. And this is done by defining the optimum torque value to maintain the optimum TSR. And this is done basically by calculating the required torque for the speed using what's known as the optimal mode gain. So once we reach rated power at this point here, then we start to pitch the blades to actually reduce the aerodynamic efficiency and so maintain the desired power and speed for the turbine. And the effect of pitching is to move these curves defining the aerodynamics through a single point, which is the rated power point. And so as the wind speed increases, we further increase the pitch angle to maintain the correct operating point, as shown. So the controller in the constant speed regions and the pitch controller, they are basically PID controllers, so proportional, integral, and derivative controller, which enables you to obtain the optimum performance given the varying conditions. So, for example, the pitch speed control loop would have scheduled gains. So the gains will be defined for each wind speed above rated. And this gives us the optimum performance and robustness across the range of wind speeds for the turbine. So in below rated conditions, then we use torque control. So we vary the torque demand to the drive based on the speed error. And then once we're above rated power, then we use pitch control to maintain the rated power level. And these two systems are operating all the time, but only one tends to be active at any one time. So this is done by using a biasing system. So we saturate the demand of say, the torque controller when we're in above rated power conditions, so that both controllers aren't trying to operate at the same time, or to provide counter demands. So this yields our steady state curves, and we can see that below the rated wind speed, then we see that the power increases, and this is the power curve up to rated power. And then once we reach rated power, we can see that the pitch angle starts to change from the fine pitch angle, which is defined for the optimum aerodynamics. And in this region, we are tracking the optimum CP by varying the torque to the required level. And then once we're outside the optimum CP range, then we fall away from the optimum TSR. So above rated, we're throwing away performance in order to maintain the correct speed and loading for the turbine. So I think the final thing in terms of the basic control that's worth talking about is the blade aerodynamics and the effect of thrust and pitch. So we can see that we have the wind approaching the rotor, and due to the rotational speed of the blade, then we have a resultant wind speed flowing across the aerofoil, which produces a lift force, and that produces components in terms of drive or aerodynamic torque. But also produces a significant thrust. So actually, when you're near fine pitch, then the thrust load is quite significant. And when you get towards rated speed and start to pitch the blades, then the thrust force from the rotor reduces very significantly, very rapidly. So this produces quite a large nonlinearity. And is a source of excitation in the turbine. So yes, the thrust force can vary, and thus has impacts particularly on the tower, and in the case of the floating platform, has an important influence on the dynamics, which we'll come to later. So the other thing to consider when we later talk about the dynamics is the effect of the turbine motion. So if the nacelle of the turbine or the rotor is moving, the rotor plane is moving into and out of the wind direction through dynamics, then this causes a change in the effective wind speed. And so we see then an increase in the lift force and an increase in thrust and torque loading. And the rotor would then accelerate. But we control that by pitching the blades. This produces a rapid reduction in thrust loading. So this concept that's useful to consider for the platform dynamics. So in terms of floating wind platforms, obviously the floating turbine and platform offers greater access to the wind resources. And there are three classical types of floating platforms. So semi-submersible, which is where most of my experience has been with, but also to a lesser extent, spar buoys and tension leg platforms. And these platforms are anchored to the seabed using flexible mooring lines. And this flexible mooring line leads to very low frequency platform dynamics, which in some cases also have very low damping levels. And this is the challenge for the control design, the interaction between the normal wind turbine control objectives and the low frequency platform dynamics. It's worth mentioning that the dynamics and therefore the control design are very platform specific. So mostly from this point, we'll be talking about semi-submersible platforms. So the low frequency dynamics challenge. So another aspect to consider is how the platform natural periods are chosen. So typically the platform period is chosen to avoid wave excitation. So this is the wave spectrum, or an example of a wave spectrum in the sort of 0 to 0.1 hertz frequency range. And so often the floating turbine platform is designed to have the platform motion at a different frequency, so not excited by the waves. Typically this is lower, and therefore this puts it into the frequency range of the wind spectrum. And so you can have a clash between the platform dynamics and the wind spectrum. So and this is basically because the turbine controller will be pitching the blades due to the wind spectrum. And this produces a change in thrust loading in the frequency of the platform mode. So this can cause motion of the platform and instability in the platform in some cases. It's also worth mentioning the turbine controller bandwidth, which is the blue box here, which is typically in the 0 to 0.1 hertz range. So this is the area where the controller is designed to be active, so positively changing the pitch demand due to the variation in the wind. So in order to maintain the speed control within acceptable bounds, this is where the turbine controller, pitch controller, is most active in this frequency range. Again, overlapping with the platform dynamics. Above this frequency, the controller bandwidth, basically the controller is designed to then be suppressing activity, have a lower response. So the way we analyze the dynamics is using a camel diagram. So we have the rotor speed on the x-axis versus frequency. And this is typically a Campbell diagram for the turbine itself. So we have the tower frequencies being the lowest frequencies. And then we typically have the blade flap-wise frequencies, a slightly higher frequency. And then we have the rotor edgewise frequencies at a slightly higher frequency again. And these may be also coupled with the drivetrain frequency, so the frequency of the flexible drivetrain that we saw earlier, primarily in the low-speed shaft, but also in the gearbox and its mountings. So the Campbell diagram also shows us where you might have potential clashes or resonances, where we have interaction between the rotor harmonics. So 1P being the lowest, so once per revolution. And this may have forcing caused by imbalances such as mass imbalance and pitch imbalance in the rotor. 3P is also a significant forcing level. Typically, this is the blade passing the tower for a 3-bladed machine. And then also typically multiples of 3P, then 6P, 9P, 12P can also have significant forcing. So when we're doing the design for the turbine, typically we're looking for modes with low damping levels, which is typically the sort of edgewise modes. So where there's very little lift force caused by the motion of the blade, or drag force, sorry. And of most interest is those modes with low damping close to the rotor harmonics, such as 6P or 3P or 9P. And particularly, again, near rated speed, where the pitch is active and causing rapidly changing thrust loads. So in terms of platform dynamics, we also use the Campbell diagram, and these frequencies are much lower than the typical turbine frequencies. So of particular interest are the modes of the platform which cause the rotor plane to move into and out of the wind, because this causes the coupling effect with the normal turbine control, and due to the change in thrust load. So it's typically the surge mode. So in this example, it's down here at a very low frequency, and also the pitch mode of the platform. So when the platform pitches fore and aft, this also moves the rotor plane into and out of the wind significantly. And this is the dynamics challenge. The coupling of the platform surge pitch motion with the pitch speed control, this can lead to platform instability in the surge pitch directions, and the turbine controller needs to be adjusted for this issue. So what we see effectively is a positive feedback effect. So when the platform pitches forward, we see an increase in effective wind speed, and so the blades pitch to feather to reduce the speed, but then this reduces the thrust, and so the platform then pitches further forwards, and then we have this positive feedback effect. So this is an undesirable dynamic for the system. So there are a number of different control loops. So as we talked about, the torque loop and the pitch speed loop. There's also a drivetrain damper typically, which damps torsional vibrations along the drivetrain using the torque demand. There's also something called nacelle acceleration feedback, which uses pitch typically to increase the damping of the tower mode, and this is based on a nacelle accelerometer sensor, and this produces an additional pitch demand on top of the normal pitch demand for controlling the speed. As we touched on, you can also have individual pitch control, which reduces asymmetric moments at the hub. For floating turbines, we also use the nacelle acceleration feedback term, which can use additional pitch or torque demand to help reduce the rigid body motion of the platform. And we're talking here about non-minimum phase dynamics. So we touch on this now. So don't intend to go into detail of the maths of this, but it's a useful way of looking at the system dynamics of the linear model. So we basically have the concept of a stable region and an unstable region. And so the poles are basically the roots of the transfer function of the system dynamics. And if they're on the left side of the imaginary axis, then the dynamics are stable. If the pole is on the right side of the imaginary axis, then the dynamics are unstable. If the pole is off the axis, but in the stable region, then you have a damped sinusoidal response. And the closer the pole gets towards the imaginary axis, then we have lower damping. So once we go into the right half plane, then we have basically negative damping. So the dynamic is unstable. That's the pole. There's also this concept of the non-minimum phase zero. And this is typically where we have a slightly strange dynamic behavior. And this tends to limit the design of the controller for maintaining speed. And this is basically the characteristic that we have with the platform dynamics. And the positive feedback effect is that we have typically have a non-minimum phase zero in the system dynamics. So what does that mean for the control design? So basically this is what's called a root locus. So this is how we design the pitch speed control loop. And the locus just shows us how what happens to the closed loop pole of the system and the controller if we vary the gain of the controller. So if we increase the gain to a certain level, then we push the closed loop pole outside into the unstable region, and we would have an instability. And this is the non-minimum phase zero, which is the cause of that. And this is due to this positive feedback effect that we've talked about with the platform dynamic. And this basically means that we have to limit the bandwidth of the pitch speed control loop, which causes larger overspeed levels and lowers the quality of the power output and can increase structural loads. So what we can do then is to incorporate this additional loop based on the cell acceleration to damp this motion. So here we have the root locus for the pitch speed control without the additional term. And here we have it with the additional term. And we can see that the root locus has been changed by the additional loop. And in particular for the pitch and the surge, we can now see that the surge is generally more stable. So the root locus is in the stable plane, whatever the gain. And the effect is to also allow us to increase the gain of the pitch speed control loop as well, which brings benefits in terms of speed control. So what are the effects of the platform stabilization? So we have, here's an example of a step in wind with the platform stabilization. So black is without any platform stabilization and the red is with platform stabilization. And this is to support structure rotation about Y, so basically the platform pitching. And we can see using this additional stabilization loop, we can significantly reduce the oscillation of the platform. And also because of the coupling between the platform motion and the pitch, we also see less pitch activity due to the stepping wind speed. So how do we achieve that stabilization? So we use the nacelle acceleration feedback. So in addition to the normal pitch speed control, we can have this platform stabilization pitch loop. So we add an additional pitch demand, which is based on the nacelle velocity. And so we can tune that loop to reduce, to apply an additional pitch demand in phase with that platform motion. And this helps to reduce the oscillation. The alternative is to use torque demand. So also based on the nacelle acceleration signal, we can vary the torque demand, again, in phase with the motion. And this also has the effect of damping the platform motion, basically counteracting the effect of the platform motion on the thrust loading. So these loops use nacelle fore-aft acceleration, which is a readily available signal on all wind turbines. So there's no additional sensor cost for including this effect. So what is the effect? So we can see in these plots how the different strategies perform. So NAF-P is nacelle acceleration feedback for pitch, and NAF-T is also using torque. And we can see the effect using either technique compared to the baseline. So we see significantly reduced generator speed variation due to the stepping wind speed. And it's worth noting that in this case, the platform is basically unstable without these additional control loops. And this is the response in surge motion using either of the techniques. Again, we see significantly improved motion, more stable motion. The difference between the two methods is really in terms of the pitching motion of the platform. So the nacelle acceleration feedback to pitch generally produces a more damped response of the platform pitch motion. The other issue with the feedback to torque is that it tends to increase the torque demand significantly. So generally the lowest cost is to use the nacelle feedback to pitch demand. And then one thing to touch on is for stable platform types where you don't have the non-minimum phase issue, or you don't have the significant coupling between platform motion and the pitch, the blade pitch. And the platform may respond to wave motion, and due to the wave motion, large generator speed variation can result between the cross coupling. So aggressive pitch control can be used to limit overspeeds, provided that the platform is of a stable design. And we can use basically a wave-dependent pitch demand. So essentially you have dual pitch control loops. And one has a very high or very aggressive gain to try and maintain the speed in those high steady states. And we can switch between the two modes using an envelope detection, which is based on the generator speed and the nacelle fore-aft acceleration. So the controller chooses the best PID based on the C state. And this has the effect of reducing overspeeds and shutdowns, and can result in a significant increase in power production and downtime for the turbine if the turbine speed variation is so great that it shuts down. Okay, so just wrapping up, what about the future? So one possible application that could be useful for floating turbines is LiDAR, which is a laser Doppler anemometer. So basically laser beams are projected forward from the turbine out into the wind field, and then they reflect back off aerosols in the wind. And that reflection can then be used to determine the wind speed at different positions ahead of the turbine. And the benefit of that is then we can use feed forward control. So where we normally have a feedback controller reacting to the changes in the wind and the turbine speed, we can also then use, using the output from the LiDAR, a feed forward term. And basically this feed forward term looks at the wind conditions ahead of the rotor and then works out the pitch rate required to have the blade pitch at the optimum angle for that wind speed when it arrives at the rotor. And this has the effect of can have the effect of significantly reducing the loads in the turbine, and also improving the speed control as you're proactively controlling rather than reactively controlling. And this can lead to reduced actuator usage, reduced variance in wind speed and power output, less turbine downtime, and also reduced extreme and fatigue loading. And I think this is particularly the case where it's particularly beneficial where you may have a lower responsiveness of your pitch controller due to the coupling with the platform motion. So in terms of load and COE reduction, some studies have been done. And my own experience suggests that this is for a fixed onshore tower, not for a floating structure, that you can achieve 15% tower-based load reductions is achievable. And this could even be even higher where you have a speed control which is affected by additional dynamics. And this could be the case for a floating wind turbine, or for, say, a soft tower, which is a very flexible type of tower, where that dynamic also means that you compromise the responsiveness of the pitch control in order to reduce the loads. We also in DNVGL did a study, the 47 megawatt baseline study, where we looked at the effect of enhanced control, which included LiDAR. And we found in that case, which was a large 7 megawatt offshore turbine, a 7% reduction in lifetime fatigue load due to feed forward control, which then went through in terms of cost of energy with some other enhanced control measures, but LiDAR was the primary one, would lead to a 2.5% reduction in cost of energy, just as an example. So feed forward control, I think, could be an important thing for floating turbines because of this compromised pitch speed control that you normally have. Could be quite effective. And in terms of future projects, research is going on, and in many aspects of floating turbines, specifically in terms of control. So we are involved in an advisory level with a float tech project, which is coordinated by TU Berlin. This is an EU-funded project, which is looking at a couple of interesting areas. So wave-based feed-forward control. So it's using a radar to measure the waves ahead of the turbine and use that to develop a additional control strategy for load reduction. And also wind farm control. So using a concept which is called active weight mixing. So this actually uses the additional platform motion that you get due to the low stiffness to disturb the turbine wakes. And this has the effect of potentially increasing the energy capture. This may well be at the expense of loads, however, turbulence. So cost of energy studies will be made to look at that. So these are sort of more longer term effects that could be influential for floating turbines. Okay, and then finally, so just in summary, we've looked at the wind turbine control concepts, and we've seen that the primary control loop is blade pitch variation for power and speed control above rated speed. And the control design and platform dynamics are highly specific, and the design is best integrated together. Often, due to the additional dynamics of the platform, having very low frequency modes and low damping coupled to the blade pitch control, this can result in less effective speed and power control with larger excursions, which has the risk of shutdowns and downtime. But additional control loops can be used to stabilize the platform motion due to the wind, and bringing in benefits in terms of speed control and reduced loading. And this is based on nacelle acceleration signals, which are standard controller signals. And this is well-established technology. In future, feed-forward control, such as LiDAR wind measurement or radar wave measurement, could offer further improvements in speed control and loading. So that is the end of the presentation part. So I believe there could be some questions to take.
Thanks, Mark. So we do have some questions for you. Firstly, we have one regarding the turbine market in general. So could you let us know your expectations of when we might expect to get 20 megawatt turbines in the UK?
Yeah, I think it's hypothetical, I would say, whether the turbines are going to go that large. So I would think that's a long-term thing, and I think there's a particular focus on cost of energy of the turbines. So it could be that actually turbines of that size are prohibitively expensive, and so the cost of energy studies may show that. So I wouldn't expect the same sort of growth in sort of turbine size that we've seen over the last sort of 15 years to continue.
Okay, thank you. Then there is another one regarding the safety system, fail-safe systems. So some Martins asked, why can we not have two PLC units, one with backup within the WTG for less disruption instead of using a fail-safe system with basic inputs?
That's a good question, and I'm not sure I know the answer to that. So my background is algorithm design. Yeah, I think that's that. I can't really answer that question. I think.
Okay.
Is there a specific benefit that's mentioned?
And nothing to add to it, unfortunately.
Okay.
Okay.
Sorry.
So another one was regarding the control systems itself. So could you give us some detail regarding how the controller might mitigate discrepancies between the simulated and real world usage?
So basically you build in some robustness into the controller. So it wouldn't necessarily see that there was a difference, but the controller ought to be stable and operate to a reasonably acceptable degree, with some difference between the modeling. and the actual turbine. And this can be mitigated to a certain extent by doing the system ID work. So I think you can then update the model and have greater confidence and possibly tighten the margins, so to try to get a bit more performance. But there should be, depending on who's designed the controller, there should be a basic level of robustness, so stability of the controller with a difference between the real turbine and the model turbine.
Okay, thank you. So we have one more regarding the feed-forward technique. So someone said it's fascinating to understand about it, but when do you foresee the introduction of wave monitoring to reduce the fatigue loading of the platform?
Yeah, as I say, I think this is a research area that's ongoing. I think the FloatTech project, I think, is a 3-year project. So I would see probably beyond that time frame, depending upon the performance that we see with it. I think that LiDAR control maybe is ahead of that. So I think certainly with onshore turbines, it's sort of getting into the certification standards. So being able to, you'll be able to certify your turbine with LiDAR. I think you can already, but I think it's getting into the standards as well. So that's a nearer term solution, which we could see the benefit of.
Okay, thank you. And Martin, who's asked the question about the PLCs, has added. So the reason for the question was because he says we have a complete PLC control system to take over control if required to allow full function to remain in place.
Okay. Yeah, I guess. Yeah, again, this is not my expertise, but I guess there's an element of it being simple and fail-safe, I guess. And I'm not sure how the sort of certification agencies would feel about having dual PLCs, although there is some redundancy there clearly. So again, I don't think I can really give a good answer to that question myself.
Okay, and we have one final question for myself as well. So we are seeing more and more hybrid technologies being considered for offshore wind turbine platforms. So do you see the optimization process being different for the control systems, especially if you're considering many turbines in a large wind farm where we are working with wake effects as well?
So I think that I think there's kind of different levels of control. So typically we see on the turbine control tends to be the type of control systems that we've seen. So sort of feedback controllers and feed forward controllers. Mm-hmm. And then in terms of wind farm control, it tends to be more about steady state set point management. So it's a different style of control. So could that be integrated? Could there be some benefit of it? I think you could look at the cost of energy, and so I guess maybe possible to reduce the cost of energy of the wind farm if you consider the design and sort of wind farm management during the design stage. But in terms of the primary turbine control, it's more likely that it would have some additional inputs than change the specific design of the controller, I think.
Okay, thank you. So we have one last question. So Ian's asked, does the temperature affect the output at all?
Of what?
I presume the turbine?
So the temperature would, I guess, if this is the turbine itself or the air temperature. So if there's a difference in air temperature, that would cause a difference in air density, and so that would affect the output and the loading on the turbine. In terms of the turbine itself, I'm not sure that there's any effect that I'm aware of.
Okay, thanks, Mark. Thank you for your time and very interesting presentation. I'd like, on behalf of Aberdeen Maritime Branch, thanks for attending today as well. And I'd like to hand over to Anastasia to close off the session.